Hey everybody, this is Josh Valentine once again with the Clean Coalition. Thanks for joining the webinar today. You are attending the fifth webinar in the Peninsula Advanced Energy Community, also known as PAEC, P-A-E-C. And this webinar is about streamlining the interconnection of advanced energy solutions to the grid. And we have Sahm White from the Clean Coalition presenting today. I would like to go over a few things regarding the GoToWebinar control panel and other technical functions. The recording and slides for the webinar will be sent to all registered attendees within the next 2 days. All webinars are archived on the clean-coalition.org website and on our YouTube channel. There will be a Q&A with Sahm at the end of the webinar. If you'd like to submit a question, we will do our very best to get to that question. If Sahm cannot get to the question, he will be in touch with you, hopefully, after the webinar. You can do so in the GoToWebinar control panel. If you enter in a question, it'll come straight to us. If you have any other questions about past webinars, this webinar, or future webinars, contact me at josh@clean-coalition.org. So speaking today is Sahm White. Sam's been with the Clean Coalition since the very beginning. He is the Economics and Policy Analysis Director. He brings over 20 years experience in economic and environmental policy with over 200 filings before the Public Utility and Energy Commissions. Prior to joining the Clean Coalition, Sahm held positions as a senior research consultant to the Center for Eco-Literacy, technical and policy analyst in the development of the ecological footprint, and associate director of Progressive Secretary, a leading web source of legislative constituent engagement. So I'm going to pass it off to Sahm now, and he's going to begin his presentation.
Good morning, everyone, or good afternoon, depending on location. If you're not already familiar with us, I'll note the Clean Coalition is a nonprofit organization whose mission is to accelerate the transition to renewable energy in the modern grid, leveraging technical, policy, and project development expertise. And Josh will be advancing the slides for us as we go, and that's appropriate. The best practices report we're covering today offers specific recommendations to improve the predictability, flexibility, and objectivity of the wholesale distributed generation interconnection processes. It does so with the goal of improving the project success rates and lowering costs directly or indirectly reflected in the utility customer rates. The Clean Coalition's work was funded by the California Energy Commission and aligns with the goals of Assembly Bill 327, which requires utilities to develop grid planning strategies and programs for the deployment of distributed energy resources, including dramatically streamlining interconnection. And next slide. We have a number of topics to touch upon, including information sharing, transparent application and review processes, predictable timelines, queue management, dispute resolution procedures, cost certainty, automation and online interconnection portals, and standardized interconnection fees. We'll start with a quick review of the opportunity for faster, cheaper development of renewables and the importance of streamlining interconnection. We'll advance the slide. First, I'll just remind us of what distributed energy resources are. These include local solar, wind, and other generation, energy storage, and combined with controllable loads and management systems connecting directly onto the distribution grid. Bringing DER onto the grid effectively and appropriately is an important part of the pathway to a cleaner, more resilient system. Next slide. Wholesale distributed generation is an important DER market segment. Behind the meter and remote utility scale resources are both part of the equation. But wholesale DER combines economies of scale with proximity to load, maximizing use of local capacity while avoiding line losses, transmission costs, and land impacts. Next slide. Germany has provided a clear example of how streamlined interconnection is an important part of effective policy for the transition to sustainable energy resources. Germany's annual additions were consistently 4 times greater than the US nationwide totals. Every single one of these required interconnection, and the streamlined processing with predictable costs has been a major factor in the actual deployment. Next slide. We'll see that the Germany's solar deployment are almost entirely sub 2 megawatt projects on built environments and interconnected to the distribution grid, but not behind the meter. Next slide. Some critics of Germany's programs tend to say that they're paying too much for renewable energy generation. But as this chart shows, comparable US efficiencies would be highly competitive. This conversion adjusts for the US tax incentives and differences in solar resources. And next slide. As we see here, avoided transmission investment costs and losses reinforce the value of local resources and the need to streamline their deployment. In the next slide, we're all familiar with the statistics of the growth of renewable energy facilities, and in particular, the growth of distributed solar in recent years, as shown in charts like this one. 120,000 solar projects were installed in California last year alone, and the state has already installed 20 gigawatts. Worldwide, over 100 gigawatts of solar will be installed this year. And again, every single one requires interconnection. So we look at the next slide. We're also aware that the total installations are not spread evenly across states or utilities, meaning that the impact on demand for interconnection varies widely today. And the issues encountered by one utility may have already been solved by another and not yet faced by others. Last year, 75% of distributed solar interconnections were processed by fewer than 5% of utilities. While most utilities still see fewer than 500 interconnection applications per year, but the future is coming fast. You see the next slide, that there is more potential than is needed to meet peak demand in most communities on existing built environments close to customer loads. By themselves, the largest 25 rooftops in Los Angeles offer a total of 75 megawatts of capacity. Moving to the next slide. This project in San Francisco demonstrates solar on multifamily housing. It is interconnected as an aggregated net energy meter project under separate metering, the same physical interconnection as wholesale projects. In this instance, you can see neighboring available rooftop space, but the PV has mapped out the circuit capacity of this location. Under a separate CEC grant contract, we are independently arranging installation of energy storage on the same circuit that will mitigate grid impacts of the existing solar and allow more PV to be installed on that circuit without upgrades. The storage will also offset its costs by providing grid services. Current limitations on interconnection standards created significant barriers, however. Despite the fact that the batteries are being installed to demonstrate that they can greatly improve hosting capacity, utility studies assume that they will have the opposite effect until certified methods of guaranteeing the operational profile are accepted by the utility. Next slide. Where interconnection happens is important to both applicants and ratepayers. The cost of interconnecting projects, reflecting the time and effort required, is highly dependent upon location. All parties can avoid high costs if information is made available. A study by Southern California Edison looking at just their share of California's interim target of 12,000 megawatts of distributed renewable generation found that if only half of these projects were guided to locate closer to the point of energy consumption, ratepayer transmission upgrade costs would be reduced by 2/3, saving over $2 billion. And distribution upgrade costs could be reduced by half. Yet few facilities are actively planning for substantial growth of distributed energy resources. A fundamental shift in the power systems requires a similar shift in grid planning, which guides the investment dollars for billions of ratepayers dollars into generation, transmission, and/or distribution. New approaches to grid planning and interconnection are needed to ensure that these dollars are efficiently invested in a smarter, cleaner, and more resilient grid. This includes recognizing the full value of distributed generation and energy resources, identifying optimal locations for deployment, and streamlining the interconnection process. Next slide. Interconnection policies and processes impact the development of distributed energy resources, hindering, guiding, or facilitating them. Meeting local capacity needs through locally interconnected generation can reduce the need for new transmission, especially where distributed energy resources are integrated to providing local balancing. Under business as usual, new incremental transmission investments in California have been projected to rise by transmission costs up to 7% per year. In 10 years, at this rate, the cost of transmission will exceed the cost of energy, and comparable costs may be seen throughout the country. These ratepayer costs can be substantially reduced or avoided, as we saw when California canceled $2.3 billion in planned transmission last year due to the higher than forecast growth in distributed energy resources and efficiency. Effective distribution interconnection is an important factor in realizing these savings. Next slide. Many states are aware that comprehensive interconnection standards are a critical component of the development of in-state renewable markets. Most comprehensive standards have multiple levels of review based on system capacity, complexity, and level of certification. In these applications, for small certified systems are processed quickly, while larger systems may require closer review. By establishing multiple levels of review, we ensure that the most common systems interconnect quickly, safely, and inexpensively without having to endure a process more suitable for a nuclear facility or a 10 megawatt combined heat and power system. However, as we saw earlier, much renewable capacity, as well as a lower energy cost, is achieved through wholesale commercial-sized systems, and efficient interconnection is at least as important for this mid-sized sector. Next slide. Interconnection is a critical facet of accommodating the growing demand for distributed resources and capturing their benefits. The goals of interconnection policy should therefore seek to efficiently incorporate appropriately cited DG in a non-discriminatory manner as a major clean energy source in a secure, resilient, and cost-effective electric grid, and help customers make timely decisions about where to apply and what the costs will be. We have several categories of mechanisms to achieve these goals, including transparency, accessibility, simplicity, speed, and certainty. New, clearly defined interconnection study tracks can serve all segments of the diverse distributed generation market. We can better understand how to implement and achieve these broad goals by looking at the types of problems we want to solve or avoid, and strategies and policies already developed and adopted to support these goals. Next slide. Distributed generation has proven extremely effective when it does not face artificial barriers in easily interconnecting to the grid. But huge potential has often been stymied by lack of information, outmoded rules, slow processes, uncertain conclusions, and no cost liability limits. For example, and why we've undertaken reforms in California since 2011, as of that year, only 14 out of the 392 applications over 1 megawatt submitted to PG&E, Pacific Gas and Electric, had received interconnection agreements. Only 6 in the prior 2 years. These took, on average, 6 months to study, but only 20 days when eligible for fast track. Next slide. The primary hurdles faced by customers applying for interconnection include, first and foremost, information about the application process, requirements, costs, and timelines, and customer access to grid information for siting and system design, but also utility response time, consistency among utility personnel, schedule delays in application review, site visits, studies, inspection, and utility construction, sometimes excessive requirements in equipment and upgrades, potentially complex contracts and agreements, disputes, and resolution processes. Utilities likewise face hurdles in processing interconnection applications, stemming from errors in application materials submitted by the customer, excessive applications and subsequent high withdrawal rates, a utility's own access to accurate grid information, the challenge of performing grid impact studies, inappropriate system designs in applications that trigger additional study, coordinating electrically related applications, scheduling field work like review, inspection, installation, as well as customer negotiation and dispute resolution. Next slide. Utilities can take effective steps to address or avoid hurdles faced in the application and review process by planning, preparing, and communicating. Utilities can anticipate future interconnection demand. They can design a flexible distribution grid to meet future uses and needs. They can provide clear, usable information to support submittal of viable interconnection requests. This includes maps and databases with accurate grid capacity info. They can make the information highly accessible, digital, online, linked, and searchable. They can standardize processing and evaluation of requests to provide efficient, rapid, consistent, and predictable study results, utilizing standard and objective criteria and moving toward automated analysis. And they can plan integrated solutions to capture benefits of local distributed resources, looking for ways in which distributed generation can support the grid, including the use of advanced inverter functionality, and to coordinate with energy storage, advanced demand response, electric vehicle charging, etc. Next slide. Clear information is also essential. Utilities can help customers make decisions quickly about where to build, what to build, and when to commit before submitting the application. This can be achieved through accountability in processes and responsibilities. All parties rely upon known rules, commitments, and timelines, and these must be clear and consistent and adhered to by parties. Clear review processes, which should emphasize predictability, flexibility, and objectivity, including screening and solution options. Certainty in costs. Applicants must know how much it will cost to connect a project to the grid. Earlier cost certainty means less risk and lower cost for developers, utilities, and consumers alike. Earlier cost determination means faster decisions. And lastly, transparency and accessibility in information. Too often, interconnection information is hard to come by. Developers, policymakers, and other stakeholders must have full and easy access to information, including interconnection studies, queues, costs, and grid maps that clarify the layouts and possibilities of electrical grids. Next slide. Having identified the primary issues faced by both customers and utilities related to interconnection application and agreement process, and a number of strategies, we found that solutions, even if uniquely implemented, reflect a broad set of principles that can be applied across utilities of all sizes to achieve efficient and effective interconnection for distributed resources ranging from a few kilowatts to 5 megawatts or more. These are summarized in the next few slides. The use of common statewide and national standards, practices, and procedures in contracts is encouraged. Where changes are appropriate to reflect local circumstances, these should be clearly identified to facilitate review. Interconnection procedures should be designed to handle the expected scale of requests across all categories of distribution-level interconnection, including residential and commercial. Self-generation for non-exporting on-site use, intermittent export and net metered credit, or exported for sale to the distribution system operator. This includes a common application and associated qualification date for review in any necessary studies. Clear and simple standards and procedures reduce errors and uncertainty, allowing applicants and applications to be handled consistently and without delay. Timely decisions avoid complications that may arise when a prior unresolved application is electrically related to a subsequent application. Clearly delineated timelines define both the applicant's and utility's responsibilities and the significance of missing a deadline, while allowing for flexibility by mutual agreement or under extenuating circumstances. Next slide. Review processes should emphasize predictability and objectivity, including screening for solution options. Simplified review of appropriate projects, default approval of conforming projects, rapid resolution of most common issues, identification of issues that will require further study if they can't be addressed through a supplemental review or simple modification, and determination of specific technical study requirements where needed. Next slide. Pardon me, and grab a drink. Clear cost determination is the overriding issue for customer decisions and for a successful interconnection process. Regardless of whether a customer is seeking interconnection for load, generation, or a combination of the two, establishing the cost of an interconnection should be timely, reasonable, consistent, predictable, and firm to the extent practical, including either standard flat rate fees or estimates with binding not to exceed provisions, as is common in customer-oriented business practices. Standardized, predictable, and appropriate fees are recommended both for application review, detailed studies, and specified upgrades, thereby addressing the needs of the vast majority of applicants. Both parties to an interconnection agreement should understand the basic needs of the other. Customers and their lenders require firm information to determine whether or not to proceed with the project. Contract provisions, such as non-binding estimates, or the potential for future additional costs to be applied after a contract is signed or a project is even in operation, are extremely problematic for an interconnection applicant. Such uncertainty adversely impacts the cost of providing electricity to the utility from impacted projects. Utilities likewise require timely action and firm commitments from applicants, where a project may impact the subsequent plans of other customers, and must meet obligations to assure that costs and risks are properly allocated to each individual customer or customer class in accord with locally applicable standards. Broader national standards should be forward-looking and consider the current and anticipated cost-effective capabilities of an increasingly intelligent grid. Communications, advanced inverters, automated demand response, energy storage, electric vehicle integration, and upgraded standards such as IEEE 1547. The utility should retain the right at no cost to the customer to provide or change equipment or adjust settings on inverters and protective devices in keeping with evolving operational standards and equipment. Requirements should not be opposed where the additional cost exceeds the projected value of those requirements over the operational life of the equipment or the project. Fees, schedules, milestones, and modest penalties support timely response from all parties to ensure projects progress through review, construction, and physical interconnection. These should be reasonable and sufficient to deter speculative applications while not discouraging interest among customers. Customers should also be informed where changes in their design or equipment may impact interconnection costs. The utility can only be responsible for cost commitments related to the design as reviewed, but can provide parameters for cost-free modification. Likewise, if a customer wishes to delay executing an agreement, the applicable costs and the review requirements may change to reflect updated circumstances. Once executed, the agreement represents a commitment from the utility to allow and or provide interconnection as specified, and from the customer to either proceed with plans or to provide timely notification of the cancellation or change of schedule. Allowing qualified and approved independent contractors to participate, perform, and assume bid responsibility for installations specified by the utility also offers the potential for reduced costs to parties. And we'll finally move on to the next slide. Far from the last, however. Effective interconnection is simple and transparent. This is a favorite slide that we've seen for years. Reducing administrative burdens is important. Removing barriers reduces costs, and paperwork is just one example. Germany, again, provides a stark comparison. Shifting to online forms also greatly speeds processing. Next slide. A survey of utilities with significant distributed photovoltaic experience found that more than half of those using online applications process those applications in less than 2 weeks, whereas few of those using paper filings manage this, with most taking more than a month. Pacific Gas and Electric will process 40,000 small residential system applications this year, actually probably higher than that, with an average time of less than 4 days from completed application to granting permission to operate. This is compared to an average of over 20 days a few years ago with fewer applications. Online forms support this. They ensure applications are fully completed, guiding applicants when information is missing. They provide efficient and accurate utility data capture and data transfer to subsequent forms and agreements, and database integration for analysis and reporting. They offer accessible application status tracking for utility and customer schedules, automated communications for customers and utility staff or between the two, verification of receipt, and faster turnaround times, often saving a week in each way for each two-way correspondence, from application submittal to follow-up requests, corrections, and final signatures or any payments. Next slide. Knowing what can go where with little or no modification to the existing grid helps customers establish realistic expectations regarding interconnection at their property, or to choose between locations to site new generation and submit appropriate designs. This is easily achieved by making grid information accessible, including public maps and data regarding existing and planned system capacities to support appropriate project siting and design proposals. Access to information early in the decision-making process, including pre-application data or meetings, supports well-planned and appropriate applications, resulting in a high percentage of successful deployments with minimal delays. Pre-application reports offer a valuable service. Next slide. The pre-application reports provide an applicant with information about existing grid equipment and constraints at a specific location. This information can be very useful in submitting a design proposal that's the best fit for that location, as well as estimating what upgrades would be required if you're planning to exceed the existing hosting capacity. Combined with a published unit cost guide from the utility, the total interconnection cost can be well estimated before an application is even submitted to the utility. Major California utilities provide 3 report options. The standard report has information readily available to the utility, including any known issues. Next slide. The primary service report offers details about the protection devices and the fault current. Next slide. And the third option provides specific data regarding the transformer and secondary service that may be required, that may also require the utility to make a site visit. If you've ever planned a project, you understand how useful this information is. Next slide. Looking to the future, we see guiding generation to where it's most useful, recognizing locational benefits, integration with other DER, and eventual potential goal of almost instant study results, fully or largely automated, including interconnection review. The next major step toward this goal is hosting capacity analysis. Next slide. I want to briefly highlight how information can greatly assist in assessing opportunities and in getting them quickly developed. California's new hosting capacity analysis will provide actual and not just estimated grid hosting capacity values with great locational specificity. Every node, essentially every street block. Next slide. Pardon me. This will include detailed hourly values to help match the different profiles of solar, storage, or other generational loads, calculated for each month of the year. It will also provide information on what the operational constraints are for any specific location, as well as helping to define what upgrades and associated costs would be required if you want to exceed those constraints. Next slide. The methodology used in California will specify how much DER hosting capacity may be available on the distribution network down to the line section or node level. This analysis quantifies the capability for the distribution system to integrate DER within thermal ratings, within protection system limits, and power quality and safety standards. This is analyzed using dynamic modeling methods built on power flow modeling software tools. These values are updated every month, and critically, they meet the standards required for utility engineers to use in reviewing applications. Therefore, both customers and utility engineers can rely on the same information. Customers can also use the published data to see how results apply to a specific technology or to limit their output to meet hosting capacity profiles. Next slide. Hosting capacity is calculated for all three-phase nodes and line sections of a radial distribution feeder or circuit. It accounts for the thermal loading limitations of the feeder's electrical components. It accounts for deviation in steady-state voltage throughout the feeder, including the impact of the, up to the limits of the impact of additional generation as studied. It accounts for the impacts of DER to protection systems, the impacts on voltage fluctuation and power quality, and the impacts of DER to operational flexibility. That is, the ability to reconfigure the distribution grid as necessary for operations. So in this sense, the value received for hosting capacity means that any capacity up to that limit has been studied and approved for the value published. Next slide. Planned future development of the ICA calculations will look to include substation level limitations connecting to multiple circuits, limitations in the transmission systems, identifying where network systems exist, potentially additional information on the secondary circuits, service drops, and service transformers, similar to what's provided through a pre-application report. It will also assess the values, and does currently assess the values for rotating machines, including synchronous or induction generation, rather than those interconnecting through an inverter. It will look to see if it's possible to include single-phase radial systems, different PV system configurations, and last but definitely not least, smart inverter functionality, starting with volt var with reactive power priority. Next slide. Interconnection practices will need to continue to evolve in response to increasing deployment of DER and the introduction of new technologies and new tools to process them. Sorry, I'm losing my voice as I continue. Nonetheless, at the same time, new functions in communications are establishing both delivery of services to the full range of markets, meeting system-wide, local, and individual customer needs. Distributed energy resource management systems and communications are both enabling and driving the distribution system into an active role in overall grid management, offering increased flexibility, resilience, reliability, and a much higher degree of resource optimization. Interconnection modeling and policies need to keep up with these opportunities in order to leverage the full potential benefits and avoid creating artificial barriers to both deployment and operation of these resources. Next slide. And finally, building upon the new ICA 2.0 hosting capacity analysis and data we just described, we'll be launching a pilot with PG&E arising from the Peninsula Advanced Energy Communities grant from the CEC, the California Energy Commission. The pilot is targeted at streamlining the utility interconnection processes for DER to copy or mirror the efficiencies found in the processes already used for net energy metering and to extend those beyond the restricted allowable net uses, including selling energy and services to both PG&E as a grid operator and into wholesale markets. This will provide much greater certainty to both the cost and timeline for interconnection, including a standard fee with no risk of upgrade charges. It's designed to utilize the enhancements that the ICA, or from the ICA, that will be implemented this summer, as well as making use of solar siting survey data in areas where that's available. The core components are defined and mapped eligibility areas for streamlined interconnection up to 1 megawatt, offering guaranteed fast track review and standardized guaranteed flat rate interconnection fee. The features of this pilot will reduce the risk and uncertainty of qualifying interconnection throughout the region, reducing associated costs and promoting simpler, faster, cheaper project development for all projects that conform to the new ICA values and data. Thank you. I think that leaves us a reasonable amount of time for questions.
Great, thank you, Sahm. So if you can just advance back to your GoToWebinar FAQ slide on slide 2, and this way I can go to our question page on my end.
We are there.
All right, one moment, please.
And I will switch to full screen.
Great. You can just bring that up in slideshow mode. That would be fantastic. All right. All right, Sahm. This first question comes from Mark Roast in Marketing and International Development at Seawave Battery Incorporated. Mark asks, do you have a plan to connect the results of the calculations to storage and demand response providers, individual and aggregators, so that they can use it as a potential demand signal for distributed energy management systems?
I'm not entirely clear what which data we're referring to there. The hosting capacity or integration capacity assessment data is static data. It's not live. It's updated every month to show what the capability of the grid is throughout the year. To know, and that defines the operational constraints within the system. Those will be available to any user of the grid for load operation, et cetera. Moving beyond that, using distributed energy resource management systems or DERMS, there is a great deal of future potential opportunity to have communication between distributed resources, including aggregate demand response and storage systems, in order to help these work in a coordinated fashion. And one of the long-term goals in hosting capacity assessment is to be able to study and model diverse or non-co-located DER operating on the same grid in a coordinated fashion. But it's going to be a few years until we have, outside of a microgrid context, coordination of DER between each other. Part of the issue there is looking at the cost effectiveness of such systems.
Thank you, Sam. Mark actually has a follow-up. He asks, can you take it to the next level to make it dynamic and real time?
Well, dynamic and real-time modeling of the operation of the grid is not something that the utilities are a long way from knowing that themselves. To some extent, they have a sense of what is happening at the substation and feeder level, but the visibility into operations throughout the feeder and at each point of interconnection isn't there yet. That can come, and many of the advanced inverters now required to be installed on new systems do monitor some grid conditions and have communication functionality that can be leveraged to provide that information. But while the systems have communication functionality, the communications networks have not yet been deployed to make full use of that. But that's definitely something that utilities should be looking at and planning for as we invest in the next generation of the grid.
Great, thank you, Sam. Let me know if you want me to repeat any or all of this next question. This comes from Michael Heiza. He's an instructor at UC Berkeley. Michael asks, in a residential area, how many nodes can each distribution feeder accept as the rooftop PVs keep getting connected to the feeder before exceeding the feeder's physical limits on IR loss capacity, heat dissipation capacity, as well as the power factor capacity, etc.?
Well, it's not a matter of of the number of interconnections. It's the total quantity, the capacity aggregated of those interconnections at each point along the grid and along the circuit. As you are closer to the substation, where there's more downstream load from your point of interconnection, and where the wire and circuit size is larger, the grid tends to be have much more capacity. The reason the ICA is being developed with the specificity down not just to each line section, but to each node within each line section, is to provide that information in great detail. But the hosting capacity value there will tell you what the aggregate capacity is, regardless of whether that is met or used up by a single application or 100.
Thank you, Sam. Bill Buchanan, CEO of Market Potential Incorporated, he asked, generally speaking, can you talk about smart inverters, the needs, the benefits, and so on?
That's a whole another presentation. The smart inverters offer a great deal of functionality that can help both mitigate the impacts of systems on the grid, and therefore allow larger systems and allow more systems onto the grid. They can also provide information, as we were just stating. So they can work in autonomous mode. They can provide information and connectivity to a grid operator or services aggregator to help coordinate the operation throughout the grid to adjust the output in a dynamic or real-time fashion. But that requires having the communication and control systems set up to utilize those functions. The functionality was built in phase 1 of the Advanced Inverter Standards and has now been implemented and is in effect. The phase 2 communication standards in California have been approved, and we're expecting the similar nationwide standards to come into play. And within 9 months, we should start seeing requirements for that. And then it's a matter of using those communication and those functions in ways which are both cost effective and properly coordinated without negatively impacting the customer. One of the unresolved issues we see is if you have an ability to control one or thousands of distributed resources through their advanced inverters, that doesn't mean that you've set up a system for compensating for that control and the services they can provide. We could talk much more about the services they can provide, but again, that's a whole other discussion.
Great, thank you, Sahm. Kevin Brem, a senior associate at RMI, or otherwise known as Rocky Mountain Institute. He asks, are there any standard interconnection agreements used over multiple jurisdictions? If not, what obstacles prevent standardization of interconnection agreements?
Interconnection agreements. Let's see. Well, and the short answer is yes, but there are so many jurisdictions. We have, both, federal jurisdiction over much of the country, but that only applies to systems interconnecting in order to access wholesale markets. Systems which are either serving individual customers or providing power to the host utility come under state jurisdiction. We've got 50 different states, each of which have multiple utilities within them. And we see in California, the Public Utility Commission, as it does in a number of other states, will set guidelines and standards for interconnection agreements, and has worked to make those consistent. But there can still be some variation between utilities. And as I mentioned during the presentation, there is a real value in using a standardized form as much as possible. However, there are differences between utilities and different locations. And the point is not to try to fit everyone into one box, but to use it, to have them be as similar as possible and clearly highlighting where there are appropriate differences to meet local circumstances. So that was a fairly general answer to the question, but that's about the best I can do in this context.
Thank you, Sahm. Claire Broom is a professor at Emory University, and she asked a question about a subject that we touch on often, that you covered in your presentation. Ascribing German higher usage of wholesale distributed systems to interconnection ease needs to exclude initial high feed-in tariff in Germany. Could you clarify your figure by year when the feed-in tariff became comparable to California rates, for instance?
It's currently comparable to California rates and has been for several years. If we go back 6 or 8 years, we would see the rate was higher, but largely that reflects higher costs in both countries for equipment costs, and the commodity costs for equipment have come down dramatically. What we saw in Germany was a rapid decrease of commodity costs driven by the demand there and the response from manufacturers competing for that. But more importantly, because of that competition, we saw a rapid decrease in soft costs and efficiencies of installers. And that was greatly supported by streamlined processes for both interconnection and customer acquisition, as well as, of course, the compensation mechanisms.
Great, thank you, Sam. All right, Mark Roast, another question from Mark. Mark comes from Seawave Battery. He asked, could you model the potential for battery storage and demand response to be managed variably via a geographic information system, or GIS, to keep the added load below limits while not hampering collection of electricity by solar systems?
Question was, could we model that capability to use storage systems? You can certainly model that, and that's important to do using the hosting capacity data, which is becoming available. You would get hourly levels based on what the minimum loads for a 24-hour period are for each month of the year. It would be possible using dynamic, autonomous on-site monitoring of the grid to see when you can actually exceed that minimum level safely. But it's one thing to model that. It's another thing to be able to control it with sufficient certainty that the grid operator will be comfortable allowing that capacity to be on the grid. We're working currently in the Rule 21 California Working Group in determining exactly what control systems will be necessary and how it can be possible to certify non-physical software or firmware control systems or communication systems to guarantee that output. But until those are in place, yes, it can be modeled, but you're going to be restricted to what can be certified. I hope I answered that question. You're welcome to follow up.
Yeah, if not, Mark, feel free to email Sahm, and his email was on the slides, but it's Sahm, SAHM at clean-coalition.org. Let's go with one more question. This one again from Michael Sia at UC Berkeley. Michael asks, do you see the possibility of a new regulation requiring the new installation of grid-tied inverters to be smart inverters with 4-quadrant driving capability?
The short answer is yes. But what was the beginning part of that question?
The beginning. Do you see possibility of a new regulation requiring the new installation of grid-tied inverters? And I'll just finish the rest of it. to be smart inverters with 4-quadrant, right?
Yeah, well, the 4-quadrant ability is largely related to the power factor component of the inverters, which they already have power. The current smart inverter requirements have power factor adjustment ratings, both static and dynamic. And we should follow up offline over what the expected additional uses for that would be. But to a large extent, I think those are already functionalities which are in place with advanced inverters.
Great, thank you, Sahm. All right, well, that concludes the Q&A portion. I really appreciate you presenting today, Sahm. I know you put a lot of time into this, and we always appreciate your insights into our work and what's going on in the clean local energy and interconnection spaces. I do want to point everybody to an article that our executive director wrote a little while back, Craig Lewis. Wrote an article on advanced inverters, and that was touching on a question that came in the Q&A session. It was posted on Solar Server, the global solar industry website, and it's called Advanced Inverters: Recovering Costs and Compensating Benefits. This is hosted on our website. We have sent out the link to all attendees, and we'll be sure to follow up with that link again. But if you'd like to do a quick search on our website or on Google immediately right now, you can find it there. But we also look for that link within GoToWebinar control panel messages. I would also like to point you to our website, to the Peninsula Advanced Energy Community webpage. This webinar is taking place under that PAEC Initiative umbrella as part of our webinar series for the PAEC Initiative. You can reach it on our website by going to our work and going to the PAEC link. We have another webinar coming up, surprise, surprise, and that will be taking place on June 20th. That'll be the 6th webinar under the PAEC Initiative, and this one is entitled Accelerating the Transition to a Clean Local Energy Future, and it's going to go over the overall PAEC Initiative, and it should be quite enlightening. So we hope to see you there, and thank you everyone for coming today, and we'll see you next time.